Welcome back. These are notes number 5 for forensic anthropology. Today's topic is going to be radiocarbon dating, also known as carbon dating, carbon-14 dating, or just radiometric dating. So what is it? Carbon dating is a radiometric dating technique that uses the decay of carbon-14 atoms to estimate the age of organic materials such as wood or leather. In our case, for forensics, it is bones, skeletons, and it's accurate up to around 60,000 years. So why do we do carbon dating? The entire point of carbon dating for forensics is a tool that forensic anthropologists, archaeologists in specific, use to determine how old skeletal remains are. Last notes we talked about, if we find a skeleton, how do we figure out if it's male or female and the general age? But it's hard to tell if the skeleton we found in the ground is 5 years old or 50 years old. And radiocarbon dating is the method that allows us to do that. This method was discovered in 1946 by a man named Willard Libby, and he won the Nobel Prize in Chemistry for it. Normally, I'd go through a review of chemistry to remind you what a carbon atom is like and how carbon-14 is different and how it's created and so on and so forth. But instead, I'm going to show you a clip from a Scientific American video on YouTube. This is the same video I would have shown you if we were still in class. I did not get permission to use it. So I'm not making this video public. It's a private video only for people who click on the link in our Google Classroom. I don't think they would mind because I would have used it in Classroom anyway. So we're going to watch that now, and that's going to show us the basics. And then we'll come back and hopefully explain how what they said helps us in forensics.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
Hopefully now you have an idea of what carbon dating is. But how do we do carbon dating for forensics? Let's see how that works. There are 3 things that we're going to need to know in order to complete carbon-14 dating. First, we need to measure the amount of carbon-14 that remains in this case, the skeleton that we find. Second, we need to know how fast carbon-14 atoms decay. And third, we need to know what was the starting amount of carbon-14 in the body when it died. So let's take these points one at a time. First, how do we find out how much carbon-14 is in the body or in the artifact in the bones that we find. Currently, scientists use a device called a tandem accelerator mass spectrometer, or TAMS for short. And this machine can tell us how many carbon-14 atoms there are and how many carbon-12 atoms there are in the bones. The original method was called beta counting, and this was developed and discovered by Willard Libby, and it required destroying a really large portion of your sample and took a long time. So it wasn't very good in terms of doing carbon dating on artifacts, because why would you want to destroy part of your artifact, let's say an old painting or a religious artifact or something like that, to find out how old it was if it meant destroying a large portion of it. The TAMS machine doesn't require you to use a big sample, and so it's much more preferable to the old beta counting mechanism. Second question, how fast do carbon-14 atoms decay? And it said it in the Scientific American video. We know the rate. Willard Libby studied this and figured it out. It is 5,730 years is the half-life for carbon-14, which basically means if you started with 100 molecules today, in 5,730 years, on average, you would have about 50 molecules left. If you waited another 5,730 years, you'd go from approximately 50 to, on average, 25 molecules. Now, they don't all just disappear at once. Over the course of those 5,730 years, carbon-14 atoms are decaying, essentially going back to being nitrogen atoms. The carbon-14s aren't disappearing. They're just no longer able to sustain having the configuration that they do as carbon-14. The half-life is known. It's been tested over and over to be verified. Our third piece of information. So far we know the current amount, which is the dead bones. We also know the half-life. What we don't know is how much carbon-14 was in the animal, in this case the human, the victim, when they died. And that's what we need to figure out. This third piece of information we need is going to require a little bit of math, but it's fairly simple math. So I'm going to walk you through the steps of how to do it. But before we do that, I'm going to show you an example of the level of math so we're all comfortable with what we need to do. Let's talk about money for a second. Let's pretend that at some point in time, somebody gave you $100. Your parents gave you $100 for lunch. And every day, you spend exactly $5 per day. You eat the same thing every day for lunch, and you spend $5. And then I ask you, can you look in your pocket right now to see how much money you have? And you have $15. So the question is, can you figure out how long ago you got the money? Now, this is exactly what we're doing with the carbon-14 dating. We are figuring out how much carbon-14 is left in the bones, and we know the half-life is 5,730 years, so we know exactly how much carbon-14 is decaying day by day. All we need is to find out how much money you were given in the first place. So let's say we have all those three pieces of information. This math is not hard at all. You should have taken $100 is what you started with, minus the 15 you have left. So you've spent $85. And if you're spending it $5 per day, it was 17 days ago that you got your money. So this is the level of math that we're going to need for carbon-14 dating. Not super hard. So let's go figure out, how do we find out how much carbon-14 was in the body when it died? So to figure out that starting amount, we're actually going to do a little trick. We are going to use the carbon-12 molecules that we know are in the body. Remember when we figured out how many molecules of carbon-14 are left in the body using the TAMS machine, it also told us how many carbon-12. And because carbon-12 is a stable isotope, that means that it's going to remain constant. The carbon-12 that is in your body has been around for millions and millions of years. In fact, likely most of the carbon that is in your body right now was at some point in plants, for sure, because that's how you got them. Possibly other animals. You might have got that carbon because you ate an animal that ate a plant. And at some point in way back galactic history was part of stars. That carbon-12 has been around forever, essentially. It's not going to break down. So whatever carbon-12 was in the body when the body died is still going to be there. Only the carbon-14 is going to be decreasing. So if we know the ratio between how much carbon-12 and how much carbon-14 is normally in a body, then we can figure out how much carbon-14 should have been there when the body died. Let's look at what those ratios are. Currently, in our atmosphere, carbon isotopes are present in the following amounts. Carbon-12 accounts for 98.89% of all the carbon isotopes. There is an isotope of carbon-13, so that has 6 protons and 7 neutrons, and it is 1.11%. If you add those two percentages, you get 100%. So the amount of carbon-14 is minuscule. It is 0.0000000001%. If we figure that out in terms of molecules, we find that for every one carbon-14 atom that exists in nature, there is 1 trillion carbon-12 atoms. During life, we've got carbon-14 molecules being gained because either the plants are getting the carbon-14 from the atmosphere, or the animals are eating the plants, or the animals are eating animals that ate plants. But we're also getting carbon-14 loss through decay. So this is a balance. We're going to have a ratio of 1 carbon-14 for every 1 trillion of carbon-12s. But the moment that organism dies, that's going to begin to change. The carbon-12 is going to stay constant, but the carbon-14 is going to become less and less and less over time because it is being lost to decay, but we're not gaining any new because it's not alive anymore. The smaller that ratio becomes, the longer the organism has been dead. I'm going to run you through a quick piece of math, so hopefully this all comes together and makes sense. So let's see how that goes. Okay, let's say we find a skeleton. We measure the amount of carbon-12 and carbon-14 that are in the bones using the TAMS machine. We find 48 trillion molecules of carbon-12 and 6 molecules of carbon-14. If we found 48 trillion molecules of carbon-12, then how many molecules should there have been of carbon-14 when the body died? You got to think back to the fact that it's a 1 to 1 trillion. So hopefully you answered 48, since there's 1 carbon-14 for every 1 trillion carbon-12s, and there are 48 trillion carbon-12s. Now let's use the half-life of carbon-14, which is 5,730 years, to find out how old those bones are. After the first 5,730 years, the carbon-14 should go to 48, where it should have been, down to 24. After another 5,730 years, it's going to go from 24, again half, to 12. And after another 5,730 years, it should go again in half, from 12 down to 6. So if we just add those up, our skeleton is 17,190 years old. This is not a victim that is new. This would be an archaeological find at this point. So you can see I made the numbers work out really nicely, and they don't always work that way. And when you start to find bodies that are only 5, 10, 50 years old, your math gets a little more complicated. And I don't want you to worry about that, because I'm going to show you in our activity tomorrow that if we can chart out our half-life of our carbon-14 on a graph like they did in the Scientific American video, we can actually use that graph as a shortcut to not do hardly any math at all and just use the graph to tell us how old the body is. So we'll go over that next time. Just understand this is a fairly simple mathematical equation, and it's based on this ratio of 1 trillion carbon-12s to every carbon-14 molecule. Now there is a problem with this carbon-14 method that for a long time was calling into question whether it was even a valid form of dating. And it's because it makes an assumption, and that assumption is fairly large. That assumption is that the atmosphere we have today, where there's 1 trillion carbon-12s for every carbon-14 molecule, has been the same throughout history. And as we know, there are varying amounts of carbon in our atmosphere over time. So the question is, can we rely on that ratio as being valid? If we're saying that we can go back 10,000, 20,000, 30,000 years ago, then this mathematical equation only works if that ratio of 1 trillion to 1 is true. So scientists don't like to assume, so they needed to verify that this works. So I'm going to tell you the two different methods of verification so you can feel confident that carbon-14 dating is a reliable measure of time. The first way that scientists used to verify carbon dating actually involved a tree. If you are familiar with how trees grow, for every year that they are alive, they get a growth ring. So when a tree is cut down or falls down, you can count the rings in the trunk to see how long it's been alive. So what they did is they found some of the oldest trees on Earth, and they've used them as verification for carbon-14. It turns out the oldest tree on Earth is called a bristlecone pine tree. They are among the oldest living organisms on Earth, but definitely the oldest tree. The current oldest tree is believed to be in California. It's around 5,000 years old. Now, they're not out there cutting down these trees to verify carbon-14, but occasionally one will die on its own, and when that happens, they do make sections of the trunk to use for scientific purposes. So what happens when they were verifying the carbon-14 dating is they would date an artifact, whether that was bones or some other thing, and then they would verify their findings by literally comparing it to wood that grew during that same year. Because bristlecone pines are so old, let's say they found bones and the bones were 500 years old, they could go to the bristlecone pine and count back 500 rings, take a sample of the wood from that exact same year that the bones supposedly were died at, and they can test that to verify that their results were correct, and that this assumption that there's this 1 trillion carbon-12 to 1 carbon-14 ratio has been constant throughout our history. So they were able to do that with the bristlecone pine, but it only allowed them to verify dates back about 5,000 years ago. So even then, there were some skeptics of carbon-14 dating who were calling into question of whether it was valid. So thankfully, we have a second verification method, and that is ice cores. In the Arctic, in Greenland, and some other places, scientists have drilled down in these big ice sheets, and they've pulled out these cores of ice. Now what happens when snow falls and forms in ice is it traps little bubbles of air. So that air, that bubble that's stuck in the ice, is literally a piece of the atmosphere from the year that it fell. And just like rings on a tree, scientists are able to actually chart out each yearly snowfall in their ice cores. They have taken the actual atmosphere from the bubbles in the ice cores and analyzed it to be able to tell the exact composition of the atmosphere throughout hundreds of thousands of years. And by doing that, they were able to verify that yes, this ratio of 1 trillion carbon-12 atoms to 1 carbon-14 atom has been constant throughout our recorded history. This has allowed us to be confident in the carbon-14 dating math that this assumption isn't just an assumption, that it also is a fact. So just to recap, a forensic scientist or law enforcement finds bones. They send them in for carbon-14 dating. They're going to take a sample from the bone and use it in the TAMS machine to find out how many carbon-12 and carbon-14 atoms are in it currently. They're going to then figure out how many carbon-14 molecules should have been in those bones at the time of death using the 1 to 1 trillion ratio. And then they're going to calculate based on the half-life of 5,730 years in order to determine how old that skeleton is. Now, it doesn't tell us how old the person was, it just tells us how long they've been dead for. Hopefully that was not super confusing. Tomorrow, I will give you an activity that hopefully walks you through the process a little better so that you're able to calculate how old some skeletons are and be able to pick from some missing people to figure out who it is. Thank you for watching these notes. Make sure you do the questions that are in the Google Classroom, and I will talk to you next time.